Hey, everybody. It's Thursday, April 15th. Hope the test went well yesterday. I'm going to be working on those all day to try to get them back to you as soon as possible. As you can see here in the aim today, the goal for today's video is to go over the free response questions that you had assigned to you over the beginning of the week. Now, you had a couple of days to do these questions, and so hopefully you got the chance to take a good look at them. But really, I just want to use this video to go through the questions, go through the answers, go through the scoring guides, and really just give a picture of how these questions should have been approached. The first question was, like both of them really were, a short free response question. This one said you should have taken about 15 minutes on it. It was worth 10 points. You had this launcher launching a dart with an initial speed v from a table at an angle, as shown above. And there you see a close-up view of the launcher. It's got a little spring to launch the dart. It says the dart exits the end of the launcher at a height h above the floor and lands a horizontal distance d from the end of the launcher. A close-up view is included that shows the dart in the launcher immediately before being launched. Inside the launcher, the dart lifts on a platform with negligible friction, and a compressed spring is released to push the dart out of the launcher. Part A of this question said a student creates the incorrect diagram shown above of the forces exerted on the dart at an instant in time after it has been launched, but before it reaches the floor. Indicate what aspect of the diagram is incorrect. Assume air resistance is negligible. Now, I think there are a few parts of this question that are critical to recognize in order to answer it. The first is that it clearly tells you here the diagram is incorrect, so you know you're looking for something wrong. I think the other important thing to realize here is it says it's showing you a diagram of the forces at an instant in time after it's been launched, but before it reaches the floor. Now, the obvious question here is, well, why are they telling you that? And the reason why they're telling you that is because they are trying to indicate to you there is no object with which this dart is in contact. It is simply in the air. And the fact that this thing is in the air means it is not actually experiencing any contact forces from other objects. If it was touching the floor, it'd be experiencing a normal force on the floor. If it was touching the launcher, the platform in the launcher would be exerting a normal force on it as well. But here, the only object this thing is interacting with is the Earth. And so that's the only force that should be acting on this dart. The answer I wrote here is the instant the dart is released from the launcher, there is no horizontal force acting on it. The only object the dart interacts with is the Earth. And so the only force acting on the object is gravity. That's it. When a projectile is airborne and it is not actually touching any objects, the only thing it is interacting with is the Earth. There is no dart force, as is indicated by this diagram. That does not exist. There is a normal force exerted by the launcher. When it hits the ground, there would be a normal force exerted by the ground, but in this case, those don't apply. And so the only force here is gravity. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll take a look at the scoring guide. The scoring guide is pretty straightforward here. I think I just want to go back to the question for a second. The key thing to notice here is it just says indicate, and it really doesn't say explain. This is way more detailed than you actually needed to provide. If you look at the scoring guide, this part was worth only 1 point. And it says here, your response accurately includes indicating the horizontal force should not be included. You literally could have just said there shouldn't be a horizontal force exerted on the dart. You didn't even need to talk about how the only force is gravity. I think you should be taking a little more of like a robust look at providing answers. But for this one, if you basically just said there's no horizontal force exerted on the dart, that's the only thing you needed to say to earn the point for this part. If you want to take a closer look at this part of the scoring guide, take a second to pause this video here and take a look. And when you hit play, we'll move on to part B. All right, moving on to part B here. Part B says a student produces the 3 possibly incorrect graphs shown below, representing the properties of motion of the dart after it is launched. And as you can see here, there's a horizontal velocity graph, a vertical velocity graph, and an acceleration graph. Another student claims that the horizontal velocity graph is not correct because the dart is accelerating, and therefore the horizontal velocity is not constant. Is the student's claim valid? Justify your answer. Now, I hope you looked enough at these graphs when we were talking about projectile motion to be able to tell these graphs are pretty much right. for the most part. The only issue that I would take here is that this acceleration, of course, is just the y direction acceleration. Having said that, though, that's really not a problem because in general, for vectors with components that are horizontal and vertical, the resultant is just the x acceleration squared plus the y acceleration squared. But what I really hope you remember from projectile motion is that when these objects are launched, there is no horizontal acceleration. There's only a vertical acceleration. And so what that tells you here is the resultant acceleration is really just the square root of the vertical acceleration squared. And of course, that means the resultant acceleration is just the acceleration due to gravity. That means this number here is negative 9.8 meters per second squared. That's really all there is to it. These graphs are correct. And so this question says another student claims the horizontal velocity graph is not correct. This kid is wrong because the dart is accelerating, and therefore the horizontal velocity is not constant. Is the student's claim valid? No, it's not. The student's claim is not valid, as the object's horizontal motion is independent of its vertical motion. And I think the important thing to realize here is that's the key point. Since the only force acting on the object is gravity, which is a purely vertical force, the only acceleration experienced by the object is in the vertical direction. There is no horizontal acceleration, and therefore the graph is correct. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll move on. All right, so looking at the scoring guide here for part B, you can see that this part was worth 2 points. You got 1 point for indicating the claim is not valid with an attempt at an explanation. So if you just said not valid, you got nothing. If you said not valid and tried to explain, even if the explanation was totally wrong, you would at least get half the points. The second point is for saying one of two things. You could have said the acceleration or the force is vertical, so the horizontal velocity does not change. Or you could have said the acceleration or force is not horizontal, so the horizontal velocity does not change. Again, at least for me, I'm always going to probably explain with a little more detail than is required for the question. And I think if you really make sure you cover all of your bases by saying as much as possible, then you'll ensure you get the points. That said, for this one, you really just needed to say the acceleration is vertical only, so the horizontal velocity does not change. That's the basic idea. Take a second to pause this video here and take a good look at this scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part C. Moving on to part C here, part C of this question says, from the instant the dart is launched until it reaches the highest point in its trajectory, the magnitude of the dart's velocity decreases. In a clear, coherent paragraph-length response, they want you to explain two things here. Number one, why the magnitude of the dart's velocity decreases until the dart reaches its highest point, and why the magnitude of the dart's velocity does not decrease to 0. Now, I want to go over the answer here that I wrote and then jump to the scoring guide, but I do think it should be noted here that I thought the scoring guide was written in a way that was a little unfair here. And the reason why I think the scoring guide was written in a way that was a little unfair here is because they really focus on the phrase resultant velocity and really want you to tie whatever you're saying about the components to the resultant velocity. And I think as we move forward here in our review and as we prepare for the test, I think it's really important to pay very close attention to when in a projectile motion problem, they are talking about velocity in general, as they are here, versus when they're talking about the horizontal or vertical components of the velocity. That's an important distinction to make, I think. Here, they're just talking about the velocity. So obviously, while to some degree in this question, you have to talk about what's happening to the vertical component and what's happening to the horizontal component of the velocity, you really got to tie it back to the overall, or in other words, resultant velocity that this thing has. And so here's what I wrote. I wrote, when the dart is launched, it is launched at an angle, which means it is simultaneously experiencing horizontal and vertical motion. Since the horizontal motion is independent from the vertical motion, we must consider the two types of motion separately. Now, let's just take a moment to stop there. I think it is really important at least to think about that. Now, I know I just said something that might seem like it contradicts that, but it's really important to understand the motions in each direction, horizontal and vertical, are independent, and that is just like a fact. It also should be noted that that is an extremely important fact when it comes to projectile motion problems, and so you're definitely going to want to remember that. Having said that, you want to really make sure you're paying attention to the way the question is asked. And in this question, they do ask about the velocity and not the horizontal and vertical components separately. So you're going to want to make sure you're paying attention to that. Moving on, I said in the vertical direction, the initial velocity is directed upward as the dart is launched at an angle above the horizontal. Since the force of gravity is acting in the opposite direction of the initial vertical velocity, it causes the dart to experience a downward acceleration, which, since it is opposite of the initial vertical velocity, causes the vertical velocity to decrease as it rises, right? We've talked about that quite a bit, that if the acceleration produced by a force is opposite the direction of the velocity, it causes it to slow down. If it's in the direction of the velocity, it causes it to speed up, etc. Since one of the components of the velocity is decreasing, the vertical component, while one of the components remains constant, the resultant velocity decreases. Eventually, when the object reaches its maximum height, the vertical velocity decreases to 0. However, the resultant velocity of the dart does not reach 0 because the dart still has a horizontal velocity. Since there are no forces acting in the horizontal direction, the horizontal velocity does not change. So the key detail here is that the total velocity or resultant velocity decreases because the vertical velocity is decreasing. It doesn't completely stop once it reaches its maximum height because it's still moving sideways, because it still has a horizontal component of that velocity. That's the key detail. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, take a look at the scoring guide. Part C here, scoring guide, was worth 5 points, as all paragraph length response parts to this test are. And so you got 1 point for saying the velocity has 2 components. You got 1 point for indicating that the horizontal velocity component remains constant while the vertical velocity component decreases. You got 1 point for indicating that the resultant velocity decreases because it is the vector sum of the horizontal and vertical components. This point is for mentioning or evaluating the resultant rather than the 2 individual components. And so if you just never mentioned resultant velocity, you still would have got 4 out of 5 here. And then you get 1 point for indicating that the magnitude of the horizontal velocity is not 0, or right, that the magnitude of the resultant velocity is not 0 because the horizontal component doesn't change. It's always non-zero. And then 1 point for the logical, relevant, and internally consistent argument that addresses the required argument or question asked and follows the guidelines described in the published requirements for the paragraph length response. Basically being logical and saying logical things. Now, if you look here, it says the velocity includes both horizontal and vertical components. The horizontal component stays constant while the vertical component decreases. So the resultant velocity decreases because it is the resultant of the vertical and horizontal components. Notice you didn't need to say here vector sum. And it says, but the total velocity can never be 0 because there's always a horizontal component that is non-zero. Again, as I've said many times, but didn't necessarily show in this explanation, the equations guide everything. And if you recognize here that when they ask about velocity, they mean resultant velocity. And that resultant velocity is given by this equation. That's really the way to go on this question. Take a second to pause this video here and take a closer look at the scoring guide, making sure you understand all aspects of the way they are giving the points. And when you hit play, we'll move on. And that brings us to part D. Part D of this question here says the dart is now launched so that it collides with and sticks to a wheel at time t1, which is the instant the dart's velocity is completely horizontal as shown above at left. The wheel is initially at rest and is free to rotate about a pivot at its center that has negligible friction, and it says here a short time later at T2, the dart wheel system is still rotating in a counterclockwise direction as shown at right. At T2 is the angular speed of the dart wheel system about the pivot, increasing, decreasing, or constant. Justify your answer. Now, this question is a little confusing, perhaps, only because we've never seen situations like this before. And if you were present at the morning meeting yesterday, you may want to listen very carefully to this, because what we discussed about this question was not necessarily right, And I did not want to give that away specifically based on the way the question was asked. I figured maybe you wanted an opportunity to think it over to realize the answer that was suggested was not actually right, even though it was pretty close. This question here says, is the angular speed of the dart wheel system increasing, decreasing, or constant? And what changes angular speed is torque. And so the question is there a torque here, yes or no? And the question says there's negligible friction. And so I would imagine most of you looking at this question said, well, there is no external torque. The only problem with that, of course, is that there is. There is a torque exerted by gravity. And that's the part about this that is a little confusing. Ordinarily, in these problems, we say that there is no torque exerted by gravity. And the reason we say there is no torque exerted by gravity is because gravity usually acts at the object's center of mass. And if gravity is acting exactly at the center of mass, then there is no torque produced by gravity because effectively the R in the equation RF sine theta would be 0. This is not exactly the same situation. And I'm going to draw this, I think, to make it a little easier to understand when this paddle that the dart is attached to is totally horizontal. And so I think the key thing to realize here is that there's an uneven distribution of mass here because the dart is attached only to one side of the wheel. And so that means if we draw the position vector R, which is always drawn from the pivot point to the place where the force of gravity on the dart is applied, which I'm only drawing to the side here just so they don't overlap, then you can see that the torque exerted by the force of gravity is going to affect this system. Now, obviously, if there was a dart on the other side of this wheel, then the net torque exerted by gravity would be 0. But because the dart is only on one side, the gravitational force exerted on the dart does cause a torque. That gravitational force causes a torque, which notice here, based on the way the force is acting, is impeding the rotation. The torque, if it acted on its own, would produce a rotation that was clockwise. The wheel, on the other hand, is rotating counterclockwise. And so this torque actually decreases the angular speed. In most cases, this seems like, and will be, like I said, in most cases, a question that looks like this will be a conservation of angular momentum problem. Is there an external torque? No, then the angular speed stays the same. Here, it's a little different only because of that uneven distribution of mass. So as I wrote here, the speed of the wheel decreases. In this case, there is an uneven distribution of mass because there is a dart on one side of the wheel and not on the other side. Since the force of gravity acts on the dart some distance from the pivot point, it causes a torque on the wheel, which reduces the angular momentum of the wheel as the torque acts in the opposite direction of the wheel's angular velocity. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll move on. All right, now moving on to the scoring guide. The scoring guide gives 2 points here. You get 1 point for indicating that the angular speed is decreasing with an attempt at an explanation, and then 1 point for indicating that there's a net torque exerted by the gravitational force of the dart opposite the direction of rotation, or they let you say clockwise here. And so the example response is the angular speed is decreasing because there is a net torque exerted by the gravitational force on the dart opposite the direction of rotation. This one is a little confusing. I think it's really important to realize in 99 cases out of 100, the systems will have even distributions of mass, meaning gravity will not cause a torque. In this particular instance, though, it does. And that's what's confusing about this. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll jump into the second question on this assignment. Second question for this assignment is a tabletop Atwood's machine. It says here, also, you get 10 points in 15 minutes. It says block A with a mass M sub A rests on a horizontal tabletop, while block B with a mass M sub B hangs from a string of negligible mass that passes over a pulley and attaches to block A as shown above. The pulley has a negligible mass and rotates with negligible friction about its axle. The blocks are at rest due to friction between block A and the tabletop. So there's no friction in the pulley, but there's friction on the table. It says here the tension in the string while the blocks are at rest has a magnitude T1, and the coefficient of static friction between block A and the tabletop is mu. Notice there is no subscript S on there. That's the coefficient of static friction, as they say here. It says a student claims the magnitude of the frictional force acting on block A must be equal to mu MAG. Explain why the student's claim is incorrect. The key detail here is that the system is at rest. It's very important to remember, and this actually comes up quite a bit in AP questions. This equation that I'm writing down here on the right side of the screen is not an equation that we use in this class. That equation is not true. This equation is true. Watch it closely. That equation is true, but it's not true without the max. It's really important to remember the static friction force changes size, and ultimately what its size is in any particular situation depends on the other forces that are acting on the object. And so the key detail here lies in the fact that the system is at rest. If you look at block A, it has two forces acting on it horizontally. It's got the tension, which they say here is T sub 1, and it has the force of static friction acting on it. And since this thing is in equilibrium, that means these two forces have to be equal. That's the deal to this question. The student is wrong because the expression given in the question is for the maximum static friction force. The expression given in the problem, mu MAG, is equal to the maximum static friction force. However, the size of the static friction force acting on an object at any time depends on the other forces acting on it. Since the object is in equilibrium, the size of the static friction force acting on the block is equal to the tension in the string, because the static friction force needs to cancel out the tension in the string. That's the idea. Take a second to pause this video here, write this down, adding any parts of this that may be missing from your own explanation, and when you hit play, we'll take a look at the scoring guide. The scoring guide here is super vague. I went into way more detail than they wanted. Notice it just says for a valid explanation of why the student is incorrect. You could have just said mu mg is the maximum static friction force, and there's nothing in the problem that would indicate that the static friction force is at its maximum value. I would hope you all remember enough about friction to have been able to tell that the static friction force had to be equal to the tension and not its maximum value, but that's the basic idea here. The static friction force changes. That's the maximum. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. I know it's pretty simple, and when you hit play, we'll move on to part B. All right, part B I just wrote down here because I couldn't take a screenshot of it to make it a normal size. But part B of this question here says block B is given a quick downward push so that block A begins accelerating across the tabletop and block B accelerates towards the floor. Basically, they're overcoming the force of static friction. The tension in the string, while the two-block system accelerates, is T sub 2. How does T2 compare to T1? Explain your reasoning. I think the most important thing to do here is to pay attention to the free body diagrams, what they would look like in both of these situations. Let's just go back to the original scenario here, because in the original picture, we knew the system was in equilibrium, and we knew the tension force in this rope here was T1. And when the system is at rest, you should know what T1 is, because for block B, there are only two forces acting on block B, and that's block B's weight and the tension. And so it's important to realize in this situation exactly what's equal. We're saying the weight of object B is equal to the tension T1. We're also saying the tension T1 is equal to the force of static friction. And so if A is equal to B and B is equal to C, that means A is equal to C as well. And so that means the weight of the hanging block is actually also equal to the force of static friction in this particular instance. Because the object is at equilibrium, all these forces got to be equal to each other. That's the basic idea. So in the beginning, T1 is the weight of object B. I think the key detail here is just that now that it's accelerating, these forces can't be equal. If the object is accelerating down, the net force is down. And we went over this quite a bit when we were talking about forces. I think it's a good way to remember to think about these things here. If the net force is down, that tells you one thing and one thing only, and that's that the downward force has to be bigger than the upward force. That's it, period, end of story. And so here, the basic idea is when the system is at rest, T1 is equal to the weight of B. But when the system is accelerating, and then you have that tension T2, the weight of B has to be bigger than T2. And so I wrote in my explanation here, tension T2 is less than T1. When the system is at rest, the tension in the string must be equal to the weight of the hanging block, block B. This is true because the block is in equilibrium, which means the forces acting down, block B's weight, must be equal to the upward forces, the tension T1. When the system begins to accelerate after the initial push, block A accelerates to the right and block B accelerates down. Since block B is accelerating down, the net force has to be down, which means the downward force, block B's weight, must be larger than the upward force, which is the tension T2. Since the weight has to be larger than tension 2, and here's the big point here, since the weight has to be larger to tension 2, but it must be equal to tension 1 must be larger than tension 2. Notice this makes sense because the weight of the block is just a constant value. It's its mass times g. That's the idea. Draw the free body diagrams. It helps. Take a second to pause this video here and write down that explanation, adding any parts of this that may be missing from your own. And when you hit play, we'll move on. All right, so this one here was worth 3 points in the scoring guide. You got 1 point for the answer, T2 is less than T1. You got 1 point for indicating that when the block is at rest, T1 is equal to the weight of block B. And you got 1 point for indicating that when the block is accelerating downward, the net force must be downward. So T2 must be less than the weight of block B. Notice they didn't really give you a point for putting it all together, or at least explaining the putting it all together part, but that's the deal. Their example response is if block B is accelerating down, the net force must be down. The gravitational force on B is greater than the tension T2. When the block was at rest, T1 was equal to the force of gravity on B, so therefore T2 is less than T1. I think another sentence was really needed to explain the so therefore part, as I wrote, but that, of course, is a matter of opinion. That's the scoring guide. Take a second to pause this video here and take a close look at the scoring guide, making sure you understand all aspects of this thing. And when you're ready to move on to the last part, hit play, and we'll move on. Moving on to the next part here, and this is the last part. It says, after block B falls a distance, the blocks have a speed v1. In a second trial, the pulley of negligible mass is replaced with a different pulley whose mass is not negligible. And the process described in part B is repeated. Basically, they give it a little push and then they accelerate. It says after block B again falls a distance d, the blocks have a speed v2. In a clear, coherent paragraph-length response, explain how v1 and v2 compare. Now, this one is a little confusing about how to approach it. As you'll see in a moment, there are actually 2 separate approaches you could take. You could talk about torques and forces and rotational inertia, or you could talk about energy. To me, I thought the cleaner approach was using energy, because exactly in the same way we were discussing the ramp rolling problems, meaning like it's going to take some energy to make the thing rotate, and so that means less is going to be available to make the thing translate. I think that lends itself really nicely to this question. Reasonable people could disagree about that, but this is what I wrote. I wrote the velocity v2 must be less than v1. Since block B is falling as the system accelerates, it is converting gravitational potential energy to kinetic energy. Notice I did not specify which kind, because it's both. In both cases, the gravitational potential energy is the same. And then I wrote in both cases again, probably shouldn't have done that. In both cases, the gravitational potential energy is the same. Since there's friction acting on the system, the work done by friction, and thus the mechanical energy converted to heat, is the same in both cases. Now, I'm going to be honest, I did not immediately think to explain that, although I think we could all agree that's not that hard to recognize that that's true. The scoring guide says that. If you didn't say that, don't feel too bad, because that's not obvious. In fact, I really don't even think it's necessary to explain the answer. But since it is true, it is something they wanted you to say. Some of the energy is converted to heat. It's the same in both cases because the mass of object A is the same in both cases. And so once the thing starts sliding, the kinetic friction force, which is just mu times m times g, does the same amount of work when the thing slides over the same distance d. That's the idea anyway. I went on to say the remaining energy, the energy that's not converted to heat, is turned into kinetic energy, which is the same in both cases. The same amount of gravitational potential energy is lost. That means the same amount of kinetic energy is gained after the same amount is converted into heat. And so it says here, when the pulley is massless, the lost potential energy not converted to heat is converted to the translational kinetic energy of the system. However, when the pulley has a non-negligible amount of mass, it will have a non-trivial amount of rotational kinetic energy when it rotates. Since some of the mechanical energy has to be used to cause the pulley to rotate, less will be available to turn into translational kinetic energy when the system begins to move. Since there will be less translational kinetic energy when the pulley has a non-trivial amount of mass, the system will gain less speed compared to the situation with the massless or effectively massless pulley. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, take a look at the scoring guide. All right, so looking at the scoring guide, they basically cover all of the bases that I just did. You get 1 point earned for indicating that the block pulley system has the same amount of work done on it by gravity in both cases. I think that's stupid. Why would you not consider the Earth to be part of the system? Of course, you could talk about gravity as doing external work if you make the Earth not part of the system, but I would just say, well, as I did, the second part here, for indicating there's the same amount of gravitational potential energy change in both cases. You get 1 point for indicating that the block's pulley system has the same amount of energy dissipated by friction. Again, if you didn't get that point, don't feel too bad about it. It's not obvious. And in my opinion, it's not necessary to say. You get 1 point for indicating that both systems have the same total kinetic energy change. You get 1 point for indicating that when the pulley has mass, there's rotational kinetic energy, and thus the blocks have less translational energy. You get 1 point for concluding the blocks will have less speed when the pulley has non-negligible mass, and then you get your 1 point for being able to write a paragraph. The example response says the gravitational potential energy of the block's Earth pulley system is reduced as block B falls, so the kinetic energy and thermal energy of the system are increased by an equivalent amount. The overall change in kinetic energy is the same whether or not the pulley has mass, since the same amount of thermal energy is produced by friction when block A moves a distance d. When the pulley has mass, some of the kinetic energy will be in the form of rotational kinetic energy, so less translational kinetic energy can be acquired by the blocks, and they will therefore have less speed. If you did an energy answer, take a second to pause this video and review the scoring guide, and when you hit play, we'll take a look at what the alternate solution of this problem said, which was all about torques. So as I mentioned here, energy was not the only approach you could have taken to this problem. You could have also talked about torques. And so this question, also worth 6 points in the alternate solution, gives you 1 point for talking about Newton's second law and recognizing that the pulley's mass increases the mass of the accelerating system. You get 1 point for recognizing that the translational acceleration of the system is reduced when the pulley has mass. You could argue same net force, more mass, less acceleration. You get 1 point earned for recognizing that the mass in the pulley gives it rotational inertia. You get 1 point for indicating that the torque required to turn the pulley affects the translational motion of the blocks. You get 1 point for concluding the blocks have less speed when the pulley has more mass, and then 1 point for your paragraph. So they said here, when the pulley has mass, it has rotational inertia. To begin rotating, it must experience a net torque. That, of course, is the torque really produced by the contact between the string and the pulley, because it's going to turn it. That force, which really is the tension, acting at some distance away from the pivot point, causes the thing to turn. It says here, this will affect the tensions on the blocks. Block B will have a greater upward tension than in the first case. The net force it experiences will be less, and its acceleration will be less. Because of this, when it falls a distance d, it will have less speed. Like I said, I don't think this is the way to go. Really, there are only two analyses you could do on an Atwood's machine: a forces analysis or an energy analysis. I think the forces analysis is the way to go 9 times out of 10. But if they're asking you about the pulley rotating, which they do from time to time, in my opinion, energy is by far the easier way to go. Rotational kinetic energy means there's not going to be enough translational kinetic energy. Is not a hard thing to say, particularly because you've been trained to do it so much when it comes to the ramp rolling problems. But with that, That's it for today. Let me know if you have any questions about these two free response questions, and have a good one, everybody.